Oscillators, a basic training by me, Nick Amy. So these next slides, we're going to talk about how quartz crystals function, so how quartz oscillators are working. We're going to focus on that because quartz is the dominant resonator principle used for most oscillators in the market at the moment. So on the top right there we have the symbol for a quartz crystal. You can see it's a square with two lines either side and two electrical connections coming off. That represents a lump of rock with two electrodes plated on either side. And what we're going to do is we're going to cut through a lump of quartz crystal rock, and we're going to cut at an angle of 35 degrees 15 minutes. That angle corresponds to what we call an AT cut, and the curve down at the bottom there shows the temperature behavior of an AT cut crystal. What you see is it's rotationally symmetrical about 25 degrees with a rollover point at -20 and +60 degrees. And so that's what it is. That's how the product behaves over temperature. And then we come to the next slide where we're going to show a simple package crystal oscillator. Here what we're going to do is we're going to incorporate that rock into a basic circuit to make a resonator. So looking at the circuit there, what you can see is the amplifier represented as a buffer in the middle, the second amplifier which is isolating what's happening on the feedback circuit from what happens on the outside world, and then we see a couple of capacitors. The capacitors are used because we're running the crystal in the inductive region of its behavior, and so the capacitors are pulling the crystal over to the point where the inductance and capacitance cancel each other out, and we're only left with the resistive losses in the circuit. A simple package crystal oscillator might be accurate to 10 to 100 ppm, might draw about 50 milliwatts, and as I said, the temperature response would look very similar to the curve down there. We can change the temperature response a little bit by changing the cut that we use for the crystal, but it's going to follow that y equals x cubed behavior that we see on the graph there. If we want to move up the technology tree from that, we've got a voltage controlled crystal oscillator. A voltage controlled crystal oscillator, we swap those capacitors for a thing known as a varactor diode. A varactor diode is a diode running in reverse bias, and so when we put the bias across it, the P and N junctions move apart, and the harder the bias, the further they move apart, and so the larger the capacitance that they represent. What we do is we have a third pin to control that, and if we put a DC voltage onto that third pin, we can change the capacitance value of the component while it's live running in the circuit. That gives us the ability to tune the circuit up and down, and we might be able to pull the circuit perhaps 100, 150 parts per million while it's running. So that gives us some way to correct the frequency or to tune the frequency, which you might do if you've got a comms system wanting to speak between two different oscillators and you want to get the two clock frequencies to be identical. So you might choose to tune one frequency up or down until it's perfectly aligned with the other one. The accuracy of these things over temperature is the same. There's no correction, so it's the same curve as we saw before, and the power draw is somewhat similar to what it was before. However, we can do an improvement because the next level up here is what we call a TCXO, or a temperature compensated crystal oscillator. And in this circuit, we're going to use the voltage controls that we had before, but the DC voltage is going to be connected to a circuit which has a temperature response, and we're going to try and make a network of components to build a temperature response which is the opposite of the temperature response of the crystal. So if we look at the graph down there, we see the blue line, which is the AT cut crystal response, so that's the frequency over temperature response of the crystal, and we see an orange line, which is what we're trying to achieve with the temperature compensation network. So if we can get the temperature compensation network that pulls the frequency down when the frequency is trying to move up by the crystal, then we can cancel each other out, and we hope that the overall network here, the full system, will have a temperature response very similar to the green line. So that would be trying to hit a zero line through the middle where one response is cancelling out the other. If we want better than that, we can shift to a completely different technology. So here we're looking at an OCXO, that's an oven controlled crystal oscillator. So if we're trying to remove the behavior over temperature, an alternative method is simply to heat it up and hold it at a very stable temperature. And that's how these products behave. So we've gone back to a simple package crystal oscillator circuit in the center, and then we put the whole thing inside a heater and we heat it up and hold it at a stable temperature. As long as the ambient temperature doesn't go above or close to the control temperature, then we can hold the temperature very, very stable indeed. And in fact, in an OCXO, it would normally be around plus or minus 0.1 of a degree change, while the ambient temperature is changing from perhaps minus 20 to 70 degrees or something like that. The other thing we're going to do here for a high-end TCXO is we're going to shift to a different cut. So we talked about it being 35 degrees 15 minutes for the AT cut, and we had that blue line on the graph. But for an OCXO, we're going to use what's called an SC cut, which is a stress compensated cut. This is actually a double rotated cut. So we're going to hold the original block of quartz at one angle, so that is 34 degrees. And then we're also going to rotate it through a second 22 degrees, and that double rotation, which is very difficult to control in manufacturing, so it does affect the price of these things, but that will give us that temperature response that we see on the graph below. Why do we want that temperature response? Well, what we've got in that temperature response is we have a flat spot that's somewhere about the 90 degree mark, and that flat spot means that when we do have that 0.1 of a degree temperature shift over while the external temperature is changing, the frequency shift that we're going to see caused by that is going to be very, very low. And we can achieve 1 ppb or even less than 1 ppb with these products. So it's a massive improvement on a TCXO or the products below. The downside, of course, is that if you heat something up, it takes a lot of energy to keep things hot, and so this is now going to draw something like a watt or 5 watts or something like that. And the last of the quartz crystal oscillator types, and to move into the next level of technology that we saw in our resonator slide, is a rubidium oscillator. And I said before that a rubidium oscillator really is about correcting for the aging response of an OCXO. So we've got the frequency stability of an OCXO, but over time that is going to change frequency. It's going to age just a tiny bit, and we can remove that by using a rubidium physics package. So let's have a little look at what's going on here. The diagram shows an OCXO, same as before, and we have this new element called the rubidium physics package. Inside here is a rubidium gas held in a cell, and we're going to excite it with microwave energy. That microwave energy has got to be that very long, precise frequency of 6.83 gigahertz. When that microwave energy hits the rubidium-87, the electrons in the rubidium-87 gas start moving from one space to another, and as they do that hyperfine transition, they give off a photon. Then we have a light detection system in here that looks for the number of photons that are being detected and gives us a signal, and then we can say that if we have the maximum number of photons on that cell, then we must be getting into the area of being very close to that frequency. If that frequency is developed from the 10 megahertz coming out from the OCXO, and we have a multiplier that brings it up to 6.83 gigs, and so as the OCXO begins to drift over a few weeks, we might see less photons received on the cell there. With less photons received, we know something's wrong, so we have a system here that then pushes the frequency of the OCXO to build it back up again to correct for that, and so we begin to have a feedback loop that's pushing the frequency of the OCXO as determined by the rubidium gas here. One of the things to note about this is that the rubidium physics package on the long term, so averaged over really long time periods like a year, it's incredibly stable. We've done it, we put one on the lab and left it there for a year, and I think we got 4.7 parts per trillion or something over the year. But in the short term, less than a second time periods, actually it's not very stable. It's quite noisy. And so there is why we have the OCXO, because the really high Q value of the crystal oscillator here is being used in the short term, and then it's being steered by the rubidium physics package in the long term. Okay, so that covers the different types of quartz oscillators and I hope gives an insight into how they work. So thanks very much. That was a brief summary of general state of oscillators across the industry, and hope for some insights into how they're manufactured and what to look out for them. There's some further reading here if you're interested, and we'll be doing a lot more of these in the future, so do check back for more.